Hello, everyone. Come on in. Yes, go ahead and chat me your first and last name. Remind everybody that you're supposed to let me know if you can't have your name seen on the internet or if you can't have your face seen on the internet. So make sure you send me an email if that's the case, and also change your username if that's the case. We've got actually, it's technically time to start, so I need to start real quick. But does anybody have any questions before we get started? There's only five of you in here so far. So, I'd prefer to have more people here yet, but of course it's completely optional. So I'm going to go ahead and begin. We are still in chapter 17. In fact, I've talked a lot about different things within the chapter. I just haven't done more than one really decent example. So I'm going to knock out the other examples that I think are critical. There's examples that I'm using that are very similar to the ones in the book, and then there's other ones that I'm skipping in the book that are more conceptual and stuff like that. Just because I'm not covering them, that does not mean you shouldn't know them and be completely understand them. It's more a matter of I'm trying to solve the more difficult problems for you in class so that you'll have a better understanding of how to solve physics problems. So I'll leave some of the more trivial ones to you, and that often means I leave some of the conceptual ones for you. So I'll try to hit on the concepts as much as I can, but that's also what your concept homeworks are about, as well as you're reading the textbook. When are we going to be able to vote on the meeting time? I gotcha. Uh, Yeah, I wish. So far, I don't think I'm going to be able to. This is pretty much the only time that fits in my schedule. I could possibly do it earlier on Tuesdays or Thursdays. I can't do anything on Mondays or Wednesdays. My days are completely swamped that day. The only choice I could have had was, like I said, earlier in the day on Tuesdays and Thursdays. But it's been my experience that people that are taking this online class can't make it during the day, but I will entertain that. I can, find something that fits in my schedule and then see by up or down vote whether you'd prefer to keep it at this time or whether you'd prefer to keep it at sometime during the day hours. And I'll send that out, and I'll just use basically whatever time the students most students can attend, or more students can attend, that'll be the time I use. I'm leaning towards thinking that this would be the appropriate time because I can get, 8, 10 people in here. But we'll see. Thanks for asking that, Nathan. Anybody else have any questions? All right, well, let's go ahead and get started. We're going to do a lot of different stuff today. I'm only doing really a couple, hopefully, I can fit them in. I'm only going to do a couple ideal gas law examples. That's because most students that are taking calculus-based physics have already had either chemistry or physics in high school or at TCC. And if that's the case, then you've already had a little bit of an intro to ideal gas law. So I usually don't cover it as much detail. That being said, the other chapters that we do, 17, 18, 19, and 20, there's quite a bit of ideal gas law stuff in there as well. So let me go ahead and share my screen with you guys and get started. As I did ask, remember everybody, you're supposed to chat me your first and last name. So please do that if you haven't already. I'll try to remind everybody to do it later uh, before we sign out, just in case anybody's forgotten. Now let's see if I can share my screen. All right. So you're now looking, of course, at my iPad screen, and I'm wanting to go into further on in the chapter temperature, thermal expansion, and the ideal gas law. The first problem we solved, in addition to talking about the atomic theory of matter and how that explains, for instance, the fact that materials expand upon increasing temperature and contract upon decreasing temperature, the fact that lattices have to form for solids that the molecules or atoms sort of roll over one another at a bigger distance apart than when they are in the solid state, when they're in the liquid state. And then if you continue heating them up farther, their vibrations are so rapid that adjacent molecules or adjacent atoms can't hold one another together. So they more or less have no affinity for the adjacent atoms and molecules. When we actually reach that point when they literally seem to have a negligible desire to group up with the other existing atoms and molecules, then they're starting to behave like what we call an ideal gas. So we're going to start off from there and go on. Actually, I opened up the book to the wrong area. So I would talk. I want to talk a little bit about thermometers and what makes thermometers versus thermoscopes. So if you find any kind of physical parameter that changes with temperature and ideally changes significantly with temperature so that you can detect slight changes in temperature, then you've got a thing that you can use to make a thermoscope. And the thermoscope is something that just physically changes when the temperature increases and physically changes in an opposite way when the temperature decreases. So when the temperature increases, it changes one way, and when the temperature decreases, it changes the other way. And until you have it calibrated, it's just a thermoscope. But then you can go ahead and calibrate it, perhaps by putting it in ice at 0 degrees Celsius, or ideally the triple point of water, which is 0.01 degrees Celsius. And that has to happen at a very specific temperature and pressure. And when you do that, you can then mark that as zero point 0.1 degrees Celsius. And then you bring, at 1 atmosphere, you bring the water up to a boil at 100 degrees Celsius. And if it's 1 atmosphere, it should be precisely on 100 degrees Celsius to probably one decimal place, 100.0. And then you take that distance where you've marked the zero point 0.1 and the 100, and you measure whatever that is, and you then say, okay, well, that distance corresponds to a change in Celsius of 100.1, or 0.01, 100.01 Celsius degrees. So you can then mark all the other individual marks, probably on the whole number degrees. So 1 degree, 2 degree, 3 degree, 4 degree, 5 degree, and maybe you make the 5 degree and 10 degree increments slightly bigger lines. But when you're done at that point, assuming it's all linear in between, then you have a thermometer. Okay, principles are physical properties that have been used in the past is the volume expansion of mercury. You've probably all seen mercury thermometers, and mercury's is a really wonderful metal that turns out to be a liquid at typical temperatures. So you can see this really shiny liquid, and it also changes markedly. Its size changes markedly with increasing temperature or decreasing temperature. And I say its size, I mean its volume. If you, however, put it in a very narrow, thin cylinder, then it's almost like you don't even have to pay attention to the volume. You're just paying attention to the linear length, and that too can be used. And that's the way a mercury thermometer works. You can also use an alcohol substance. Toluene is another substance we use. A lot of times there's substances that aren't good for you. Mercury's not good for you. Toluene's not good for you, and some of the other substances aren't good for you. So normally when you break one, you want to not necessarily just go willy nilly wiping it up with your hands or putting it on your shirt or something like that. Uh, that being said, we actually can then, for instance, consider other measures. Like you could, for instance, consider the volume of a gas as the parameter upon which we're going to base a temperature scale. So you could take a fixed container of gas, and by it being fixed container, it has a fixed number of molecules in it, and it's a rigid container. So in some sense, you can sort of think of it as having a fixed volume. Let me draw a picture of this so y'all better understand. So what you can imagine is a tank like this that has a very specific volume, but then you're going to have a tube like this, and this tube can actually have mercury filled in it or some other substance, but mercury is a pretty nice one. And what you can do is you always adjust this height so that these two levels of mercury here and here are at the same level. Therefore, the volume in this tube and in this rigid container here is fixed. So as long as you keep those two levels the same, you'll have a fixed volume. And since the gas can't escape through the mercury, you also have a fixed number of molecules. And as the temperature increases, what will happen is the actual pressure inside of this gas chamber will actually get larger, and that'll tend to push the mercury down and this side up, and then you can readjust it so that the levels are back the same, and then you've managed to maintain a constant pressure, excuse me, a constant volume. And in so doing, what you discover is the pressure, which is the difference between how high this level of mercury is on the left to how high this level of mercury is on the right. That's going to be a change in pressure given by the density of the mercury or whatever the substance is times gravitational acceleration times the height difference. So rho GH is the difference in pressure between these two heights. But the main thing is you're always going to adjust the mercury so that it always hits the exact same level in the left-hand tube, and higher pressures are going to force that mercury to be at a slightly different height from one side to the other. When you do that, then you'll see that evidently pressure is directly related to temperature, and you can use that as a measure of temperature. Uh, we've done things like this before. That's another type of thermometer. In fact, there's been a graph that we've made in the past where we're studying all the gases, not just a particular gas, and we make a volume versus temperature with a totally unrelated object, of course. You make a volume versus temperature graph, and a neat thing occurs. If you, for instance, were to plot the volume versus temperature curve for water vapor, you would get a straight line that goes like that. Now, if you did it for hydrogen gas, you get a straight line that goes like that. If you did it for, say, helium gas, you'd get a straight line that goes like that. If you did it for some other gases, you would get a straight line that goes like this, and so on and so forth. And what we discover is that no matter what substance, no matter what compound, no matter what element, gas we use, we're always going to have the curve. If you follow it back to the place where ostensibly the volume would become zero, you would find that all of the substances on Earth all converge at this one point right here. And that gives you some idea that there exists a very specific temperature that is, in some sense, universal and important. And you probably know, for instance, we based our Celsius and Fahrenheit scales on water, such that the boiling point of water is 100.0 degrees Celsius or 212 degrees Fahrenheit, and the freezing point of water, and I'm going to leave off the word water. I'll just repeatedly say boiling and freezing. But the freezing point of water would be 0.00 degrees Celsius. And I may be overshooting our understanding of that. It might not be 0.00. Maybe there's only one zero. Maybe there's three zeros. Not really sure. I haven't checked experimentally how well we know that for a given pressure. Additionally, the other side is 32.0 degrees. And again, I'm not sure that that's one decimal place zero or two decimal places zero or three decimal places zero. But the main thing is roughly to the nearest whole number, the temperatures of boiling and freezing are 100 Celsius and 0 degrees Celsius for boiling and freezing, and 212 degrees Fahrenheit and 32 degrees Fahrenheit for Fahrenheit scale. The difference, by the way, between these two extremes is 180 Fahrenheit degrees. Notice I wrote the degree after the F symbol there. And the difference between these is 100 Celsius degrees. Okay. Now, that's a sort of a bookkeeping measure that we use in physics and chemistry to remind us that, hey, if I see instead of Fahrenheit or instead of degrees Fahrenheit, I see Fahrenheit degrees, or instead of degrees Celsius, I see Celsius degrees, then that's a symbol to tell everybody, hey, this is not an actual temperature. This is a difference in temperature that we took by doing a subtraction, basically. Okay. But that's going to come in handy later because what we see is that for every 180 degree Fahrenheit degree change, you're going to experience a 100 Celsius degree change. That can be reduced to 18 over 10. It can also be reduced to 9 over 5. It can also be reduced to 1.8 over 1, so on, so, or excuse me, yeah, 1.8 over 1, so on and so forth. And that's going to come in handy later when I teach you a way to convert between Celsius and Fahrenheit. So, because of this unique phenomena where all gases tend to converge back at the same point, we have determined that point to be absolute zero. Okay. And it's absolute in the sense that if we found an alien species from a different star system in our galaxy, or even in a different star system in an entirely different galaxy, there's a high likelihood that they would have something exactly equivalent to our 0 Kelvin, and they might call it, Jabba or something. Just make up some random alien words there. Okay. And it might not even make a sound. It might be something that they telepathically discuss or whatever. But the main thing is they would have something like that. And in that sense, it's not an arbitrary temperature scale. That's why we have, for instance, the angular measure in a circle is measured in degrees. The measurements of longitude and latitude are measured in degrees, and we have temperatures measured in degrees. The degree is something we've used as an indicator to tell everybody, hey, this is an arbitrary scale. We made it up arbitrarily because it turns out you can think of it as like the base 60 number system or something like that. If you're actually using that, then you'd want a number that is really similar to 60. And in fact, you could make up a number system in which the number of measurements around a complete circle might be 3,600 instead of 360. We ended up going with 360. Okay. And that's mainly because, like I said, the number 360 has a lot of factors that go into it. So, for instance, it's even, so 2 goes into it. It's a multiple of 3, so 3 goes into it. It's a multiple of 4, so 4 goes into it. It's a multiple of 5, a multiple of 6. Not a multiple of 7, but I think it's a multiple of 8. So on, yeah, it's definitely a multiple of 8. So on and so forth. So that's why that was a fairly arbitrary system that we use for degrees in angular measure, and that's also why we use the degree in temperature because it was based on water, which is somewhat arbitrary. We might, in principle, find a species that maybe doesn't use water, or water's not as important to them as it is to us, in which case the water would seem kind of a ridiculous thing to base our temperature on. Not sure about that. Silicon-based life, maybe it uses dilithium oxide. I don't know. If that's the case, then dilithium oxide would be important to them. I just don't know. So, anyways, that's a little intro to the various ways you can measure temperature. So, I've already talked to you about how the coefficient of linear expansion and how objects expand. So, we found this formula delta L, meaning the change in length of an object, and that would be L final, which we call just plain L, minus L initial, which we call L zero. We found that this change in length is proportional to the initial length, L zero. It's also proportional to the change in temperature, which would be T final minus T initial, which we just call T minus T zero. And what we've done is we've made the coefficient that makes this proportional equation, or this proportionality into an equation, is what we call the thermal coefficient of linear expansion, and it's given the symbol alpha. So this is the thermal coefficient of linear expansion. And there's a table for that in your textbook where it has those specific quantities in it for various substances. And we've talked about that before. Now, you can also rearrange this, even though this is an equation that's useful to use. There's another one that a lot of people tend to use, so I'm going to show you that as well. That equation would be taking the L minus L0, which is what the delta L is equal to alpha L0 delta T. And of course, remember the delta T would be T minus T0. Now I can put the L0 on the right hand side, then I'd have L is equal to L0 plus alpha L0 delta T, or finally I could say the final length after the increase in temperature or the decrease in temperature would be equal to the initial length times 1 plus alpha delta T. So that's the other version we use. And because we're going to cover it in a little bit anyways, I left a little space in the notes to do it. But there's also a formula when you're talking about instead of just a single dimension, like this pencil, if I heated it up, obviously the length is going to go get bigger this side and this side. But in reality, this dimension's also going to get bigger and this dimension's also going to get bigger. It turns out that any physical object, when you increase the temperature, is going to tend to expand, and it's going to expand in every dimension it has. Okay. So let's go on and try solving some physical problems. I just hinted at how we're going to go about doing temperature conversions and stuff of that sort. I will tell you that there's a mnemonic poem that I learned when I was teaching metrication to Blackwater. Blackwater's a group of well, it's a business that happens to be in Moyock, North Carolina, and the government's used them to be security and stuff like that. It's mostly a bunch of retired or former military, and they do a lot of military and police type training. But anyways, I was teaching their machinist how to use the metric system, and I run across this really nice poem for temperature, and it is this: 30 is hot, 20 is nice, 10 is cold, 0 is ice. So that's just a good, shot over the bow to give you a rough feeling for the Celsius temperature scale. If you're like me and you didn't grow up with Celsius around you too much, you don't really have a feel for whether, human body temperature is on the order of 30 or on the order of 50 or on the order of the middle between or whatever. So that'll help you a little bit. Now, what I did point out was that the difference in the temperatures between freezing and boiling would be, for instance, 180 Fahrenheit degrees per 100 Celsius degrees, which, as I said, could be written as 18 over 10. Again, Fahrenheit degrees over Celsius degrees, but that also could be written as 9 over 5, and it could also be written as 1.8 over 1. Okay, the key thing to remember is that when you write it in the 9 over 5 version with the bigger number on top, in other words, that's Fahrenheit over Celsius, and that's the key to remember how to use this. Now, there does exist really nice formulas for converting between Fahrenheit and Celsius. We're going to actually skip using that, even though I'm going to offer you a chance to, for extra credit, to actually derive such equations. But we're not going to use that because we found through education research that students are better able to grasp and understand the Celsius scale by doing it the way I'm getting ready to teach you to do it. Now, I will say that because of this absolute zero, there's a very simple formula for temperature in Kelvin. The temperature in Kelvin is equal to the temperature in degrees Celsius plus 273.15, like that. Okay, so that is the relationship between Kelvin and Celsius. I should say that the British system has a equivalent to the Kelvin system, and it's called Rankine. Rankine. You can look that up, but I'm never going to ask you any questions about that. You might somehow get in a job where they need where they use that, but I can't imagine it. So let's go ahead and solve this problem here. Chapter 17, example 2. Suppose the supposed human body temperature is 98.6 degrees Fahrenheit. What is this temperature in Celsius? Solve this not by using some formula that converts between the systems, but by making use of the facts that the boiling point of water is 212 and 100 degrees Celsius, and that the freezing point of water is 32 degrees Fahrenheit and 0.00 degrees Celsius. Notice I put an underline under that zero. That's me trying to show you that 100 is 3 sig figs, and not having to just put a decimal point floating out there on the end. So I put another digit past it, but then I underlined it because when you see an underline on a digit, you should interpret that in my class as a non-significant digit. So all the digits that aren't underlined are supposed to be significant, but not that one. Okay. For part B, which I don't know why it said B twice, that's just me explaining an extra credit that you can do on your own. So we're not going to actually solve that right now. But what I'm going to do is first, I want to know how far 98.6 degrees Fahrenheit is from one of those two key temperatures, and there's actually more than two key temperatures: freezing point of water, boiling point of water. There's two of them, but there also, for instance, is a common point where the Celsius degree and the Fahrenheit degree have exactly the same numerical value, so you could do relative to that. And I usually do it from the zero, but I can imagine if I was doing something around 250 degrees Fahrenheit, I would probably use 212 instead of the zero. But here I'm going to say how far is 98.6 from, or how far 98.6 degrees is from freezing slash boiling. Okay, and I'm saying slash because, like I said, you could use either one, but I'm going to use freezing. So that's the first thing I want to do is see how far it is. Well, the freezing point within the Fahrenheit scale is 32, so that means 98.6 minus 32.0 is what we're wanting here. So 90 minus 30 is 60. 68 minus 2 is 66. So I'm looking at 66.6. Now that I've subtracted two Fahrenheit temperatures, I get Fahrenheit degrees. That's that little bookkeeping method I was telling you. Now that is 66.6 Fahrenheit degrees above freezing. And that's important. You need to know whether it's above or below whichever temperature you use. In this case, I used freezing and it's above it. If I would have used boiling, then I would have had to say it's below boiling, and I would have did 212 minus 98.6. Okay. Now, step two is how far is that in the other scale? So this is where I use my 9/5 scenario. Remember, it's 180 Fahrenheit degrees over 100 Celsius degrees, which is also equal to 18 over 10. It's also equal to 1.8 over 1. It's also equal to 9 over 5. But in this case, I've got Fahrenheit degrees on the top, so I want to use it upside down. I'm going to say 66.6 Fahrenheit degrees. And just like we do with our unit conversions, I always recommend you write it as a fraction first. So I'm going to do the same thing. And now I've got to use, let's just do, because I'm going to use a calculator anyways, it doesn't really matter. I'm going to use 1.8 Fahrenheit degrees in the bottom and 1.0 Celsius degrees on the top. So now I can take 66.6 divided by 1.8 gives me 37.0, and that is Celsius degrees above freezing. So now I say part three, what is what is this temperature are in degrees Celsius? So all I have to do is say, well, it's 37 degrees Celsius above, or 37 Celsius degrees above the freezing point of water. And in the Celsius scale, the freezing point of water is zero. So the temperature is 37.0 uh, Celsius degrees plus zero Celsius degrees, which gives me 37.0 degrees Celsius, and that is what 98.6 is in the Celsius scale. Anybody have any questions on that? Now, I can't tell when you're actually doing this like on a test. I can't tell whether you're doing it this way or not, but I will tell you that this has been infinitely helpful to me. I was the one that just, would go ahead and derive the formula anytime I needed it by using y equals mx plus b, and then I just apply the formula. That was pretty cool, and I enjoyed doing it, and I could do it really fast. But to be honest with you, this has made it where I can now do conversions in my head rather quickly, and I feel like I have a better understanding of the Celsius versus Fahrenheit. Now that we have Celsius, if we wanted to know what that is in Kelvin, we just add 273.15 to it. So, and I should call that 273.15, not 273.15. You're not supposed to use and except for the decimal spot. All right, now that I have that, let's try another example. Does anybody have any questions on that one before I go on? Okay. So again, without using a formula, convert 20 degrees Celsius to Fahrenheit. So that's, notice that's part of the mnemonic. I said 30 is hot, 20 is nice, 10 is cold, 0 is ice, and this 20.0 is a classic point. So first, I want to figure out is how far is this from freezing? So how far from freezing. Notice I'm doing the exact same questions no matter which conversion I do, from Fahrenheit to Celsius or from Celsius to Fahrenheit. So how far from freezing slash boiling? And again, like I said, if you happen to know, I think it was negative 54 degrees Fahrenheit is negative 54 degrees Celsius or something like that. There's one temperature at which they're exactly the same. If you use that, you could do that one as well. But how far is this temperature from freezing or boiling? I'm going to choose freezing. So I know that 20.0 degrees Celsius minus 0.0 degrees Celsius is equal to 20.0 Celsius degrees. Notice I put the degree again after the C. Part two, how far is this in the other scale? I didn't need that S there. That was me starting the next word. Other scale, whoa, slash system. So now I'm going to take 20.0 Celsius degrees, put that over 1, and this time I do want the Celsius in the bottom and the Fahrenheit in the top. So I could use 9 over 5. This would be 9 Fahrenheit degrees divided by 5 Celsius degrees. That's really nice because 20 divided by 5 is 4. 4 times 9 is 36. So I'm going to call this 36.0, and this will be now, because the Celsius canceled out, it'll be in Fahrenheit degrees. Now, part three here, I want to know how far or what is this temperature in Fahrenheit. So this is above freezing. So this 36.0 Fahrenheit degrees above freezing means it's 36.0 Fahrenheit degrees above Fahrenheit's freezing. So now I'm going to take the 36.0 Fahrenheit degrees and add to it 32.0 degrees Fahrenheit. And you can see that you're going to get 68.0 degrees Fahrenheit. And yes, that is a wonderful temperature. As a fat person, I thoroughly enjoy the temperature of 68 degrees Fahrenheit. Anybody have any questions on that? All right. Now, uh, it turned out that when we were going through the early discoveries of thermodynamics and stuff along that line, we sort of neglected a fundamental principle and we had to go back and fix it. So later we'll learn about the first law of thermodynamics and the second law of thermodynamics and even the third law of thermodynamics. But it turns out that we forgot something, and the zeroth law of thermodynamics is what we forgot. So the zeroth law of thermodynamics says if A is in equilibrium, thermal equilibrium with B, and A is in thermal equilibrium with C, then B and C are also in thermal equilibrium. So I just, upon stating that, said use the zeroth law of thermodynamics to tell me everything you can conclude if your arm is in thermal equilibrium with your desk surface and your desk surface is in thermal equilibrium with your pen that has been resting on it all day. So can anybody give me a conclusion they can reach from the zeroth law of thermodynamics on after this?
Your arm is also in thermal equilibrium with the pen.
Exactly. Your arm, it seems almost stupid, like you didn't need to do it, but that's also like the reflexive principle in geometry. So your arm is in thermal equilibrium with the pen. Now, you also might think it's really goofy, but to be honest with you, the thermometer doesn't work unless that happens, right? What you do with a thermometer is you take it and you stick it in some substance until it reaches thermal equilibrium, and then that gives you the temperature. And then in the process of making the thermometer, you do that and you say, okay, what's in thermal equilibrium with freezing water right now? So that's 0 degrees Celsius. And then you put it in thermal equilibrium with boiling water and you say, okay, that's 100 degrees Celsius. And then it's all calibrated. Now, if you put it in something else and it reads 0 degrees Celsius, you're going on the assumption that just because you were in equilibrium with the 0 degree water, that now that new substance that happens to be what you think is 0 degrees is in thermal equilibrium with it as well. And it has to be in order for the actual thermometer to work. Now, I will tell you that thermal equilibrium just means the two objects have the same temperature. Okay. It's not about internal energy, it's about the temperature. So if you put two objects in contact with one another and they have different temperature, then the hotter object is going to begin to heat up the colder object, and the colder object is going to begin to cool down the hotter object. Okay, so that's what thermal equilibrium is, and it's called equilibrium because when they're in thermal equilibrium, they're the same temperature, and then heat does not flow from one to the other. They just sit there as if neither one's even touching the other. Now, let's go on to the next example. So now we're going to make use of that linear thermal expansion equation. It says a 200.0 underscore meter long bed used for a suspension bridge is made of steel and concrete, which have the same thermal coefficient of linear expansion, and is installed when the temperature is 10 degrees Celsius. By how much will the bed expand and contract if it reaches 40.0 degrees Celsius and negative 30.0 degrees Celsius? Notice the zero after the decimal again has an underline in it. That's just to remind you guys that that one's not a sig fig. So the formula we're using here is going to be delta L is equal to L0 times one. Oh, not that. I'm going to do the other version. So I'm going to use L is equal to L0 times 1 plus alpha delta T. In the case of steel and concrete, the linear coefficient of thermal expansion is actually about 12 times 10 to the negative 6 reciprocal Celsius degrees. So that's what the units are, and you should be able to tell that just by looking at the fact that you're adding 1 to alpha times delta T. Delta T has to have temperature has to have units of Celsius degrees, and alpha times delta T has to be unitless. So that's why that's that way. So let's first off calculate how long the 200-meter bed will be at 40 degrees Celsius. So I'm going to say at 40.0 degrees Celsius, L is equal to 200.0 meters times 1 plus 12 times 10 to the negative 6 reciprocal Celsius degrees times 40.0 degrees Celsius minus 10.0 degrees Celsius. Notice this 40 minus 10 is the kind of thing that would give me Celsius degrees instead of degrees Celsius, just to make sure y'all understand what I was talking about earlier. So 40 minus 10 is, of course, 30. 30 times 12 times 10 to the negative 6 gives me 0.00036. I'm going to add that to 1. That gives me 1.00036. And now I'm going to multiply that by 200. And that gives me a total length of 200.072 meters. Now remember, we had only sig figs up to the ones place, not to the tenths place, not to the hundredths place, and certainly not to the thousandths place. But in order for us to make a measurement that's even remotely readable, we have to assume that we can ignore the sig fig digits, the sig fig information. What this is telling us is that the whole 200-meter length of the bed that was used on the suspension bridge is now 7.2 centimeters longer. Remember, if you move the decimal 2 places to the right, it's in centimeters. So this is 7.2 centimeters longer. Now, if we try at negative 30.0 degrees Celsius, we're going to have L is equal to 200.0 meters times 1 plus 12 times 10 to the negative 6 reciprocal Celsius degrees times negative 30.0 degrees Celsius minus 10.0 degrees Celsius. In this case, I get negative 30 minus 10, and that, of course, gives us negative 40 times 12 times 10 to the negative 6. That gives me negative 0.00048. I'm adding that to 1. That's going to give me 0.99952. Now I'm going to multiply that by 200, and that gives me 199.904 meters. Again, we don't have a sufficient sig figs there, but you can see if I subtracted that from 200, I would find that that's 9.6 centimeters smaller than 200. So the whole swing is from negative 9.6 centimeters to positive 7.2. So 9.6 plus 7.2 means the whole thing is going to move a net of 16.8 centimeters. Anybody have any questions on that one? All right. So that's pretty straightforward, right? Now, this is more of a conceptual question, but I just wanted to make sure I covered it so you guys would know. Uh, the rule that we use when we're talking about expansion due to thermal expansion, in other words, heating things up. For instance, if I had, let's imagine that this phone here is a rectangular plate. Okay, it's a rectangular plate this tall, this wide, and this thick, right? Now, what we mean by that is if I heat it up, This dimension from here to here is going to increase. This dimension from here to here is going to increase, and this dimension from here to here is going to increase. So literally every dimension increases. So now what we want to do is imagine this rectangular plate, and let's imagine instead that we've cut a perfectly circular hole out of the middle of it. Now we heat it up. Since every dimension increases, does that mean the hole inside is going to get smaller, or does that mean the hole inside is going to get bigger because that's a dimension as well? Anybody know the answer off the top of your head?
The hole would get larger, right?
Yes, that's exactly it. And the way we think about it and the way that hopefully will make it make sense to you guys is the hole that you cut out of the plate acts just like the uh, the piece of plate that you removed. So if you actually heated up the little circle that you punched out of that rectangular plate, you know that that circle would increase its diameter this way and this way. So that's how it behaves. If it didn't behave that way, you'd get weird things like when you heat up that rectangular plate, some part of it in the middle would actually get less thick because it's actually trying to fight the expansion that's going on for the plate around it versus the contraction of the metal plate that's inside the circular hole. And there was never even made a circular hole, so it wouldn't make any sense. Does that make sense to everyone? So the hole gets larger. Now that's good because that's exactly why if we're trying to open, say, a pickle jar or some curry sauce, like your book has a picture of, it's actually not curry sauce, but it's something like a curry type sauce, or a curry, I should say, not sauce. But anyways, if you're trying to open a glass jar like that with a metal lid, one way you can do it is you can take the metal lid and hold it under the spigot of water while hot water's running, and though the hot water is going to heat up the metal lid and the glass jar, glass has a smaller linear coefficient of thermal expansion than does metal. So the glass won't expand very much, but the lid will, and that'll loosen up the thread so you can loosen it. The only downside, of course, is now the lid is soaking wet and a lot harder to get grip on. So these are the problems that us old people deal with when when we get older. It's like none of our muscles are working like they're supposed to. We can't grip things like we're supposed to, and we got to think about things, how to fix them. We call it working smarter, not harder. But I'll be honest with you, it really is just a pain of aging. All right, now let's apply the same equation that we just used, but to a slightly more robust problem. So this slightly more robust problem is this listed here. It says an iron ring is supposed to fit over a cylindrical rod with a snug fit. At 20.0 degrees Celsius, the diameter of the rod is 6.445 centimeters, and the inside diameter of the ring is 6.420 centimeters. To fit snugly, the ring's inner diameter must be 0.008 centimeters larger than the rod's diameter. At what temperature must the ring be heated to fit snugly? So what we're trying to use here is we're going to use the understanding that we got from that plate a second ago and realize that a hole in a ring is going to get bigger when we heat it up. So we're going to treat that hole in the ring just like it was a chunk of steel in that hole, and we know that the hole in the ring is going to behave just like that chunk of steel would have. Okay. So what we're trying to do is take a 20.0 degrees Celsius ring whose inner diameter is 6.420 centimeters, and we're going to try to create by increasing the temperature a inner diameter of 6.428 centimeters so that it will be big enough to fit snugly. So let's go on, and again, this is iron, so we still get to use the same coefficient of linear expansion, 12 times 10 to the negative 6. So what we're going to do now is we're going to say the new length is, which is the diameter, is supposed to be 6.428 centimeters. The original length, we're using that same formula we used earlier, which is L is equal to L0 times 1 plus alpha delta T. Okay, so the original one was 6.420 centimeters, and then that has to be multiplied by 1 plus 12 times 10 to the negative 6 reciprocal Celsius degrees times this time it's T minus 20.0 degrees Celsius. So, first thing I'm going to do is divide both sides by 6.420. So, if I do take 6.428 and divide it by 6.420, I get 1.0012 4 6, and I'm keeping way more sig figs than I'm supposed to. Dividing 4 sig figs by 4 sig figs should only give me 4 sig figs, which means the 2, the 4, and the 6 are not sig figs. But and also the centimeters cancel out, so that's good. That's supposed to be equal to 1 plus. Now we're going to say this is 12 times 10 to the negative 6. Let's ignore units for a second, times t minus, now I'm going to take that 12 times 10 to the negative 6 and multiply that by 20, and that should give me 0.000240. And of course, that's Celsius degrees times reciprocal Celsius degrees. So the 1 and the 0.00024 are literally just pure numbers. So I'm going to go ahead and subtract 1 from both sides, and then I'm going to add 0.000240 to both sides. Oops. So now I get point, point 0.0001246 plus point 0.00024. That gives me, oops, hold on, that is not right. I did something wrong. Point 0.000, oops, excuse me, that was why. 0.001246 plus 0.00024 gives me 0. Oops, I'm not writing in red. That gives me 0.001486 equals 12 times 10 to the negative 6 reciprocal Celsius degrees times t. So if I divide both sides by 12 times 10 to the negative 6 reciprocal Celsius degrees, then I will get Celsius degrees, which is really no different than degrees Celsius. It's just a helpful bookkeeping method. So now I'm going to take this and divide it by 1, 2 times 10 to the negative 6, and that gives me, that is not what I expected to get. 0.001486. Did everybody get 0.001486 when they were doing their calculation? I just want to make sure because this number's not coming up what I remember it to be. Let me try again. 0.001486 divided by parentheses 12 times 10 to the negative 6. Yep, that's what I'm getting. So it turns out that this new temperature happens to be 123.3, or excuse me, 0.83. Did anybody second that answer? Degrees Celsius is equal to T. So that's supposed to be what the answer is. I remember getting a starkly different answer before, so I'm going to put a little question mark by there to get you guys to remember to check your arithmetic, make sure you agree with all the algebra I did and the arithmetic results that I got. Oh, wait a second. No, no, that's right. That's right. 12 times 10 to the negative 6, 12 times 10 to the negative. And then when I did 12 times 10 to the negative 6, that became a negative, so it became positive. Yeah, everything looks okay here. Yeah, and that's it. All right. So evidently, again, all the sig fig stuff has to be thrown out the window because I just went willy-nilly with it on this one. So we can't really trust the sig figs, but you can imagine that it's going to be on the order of 120 Celsius degrees that we're going to have to bring this ring up to make its diameter fit snugly around the rod. So does anybody have any questions on that? And I'm thinking that might be the same numbers I had when we did a similar problem in your textbook. Because remember, I told you these problems are very similar to the ones we had. And with that one, I ended up getting like 400. So that's what's concerning me. Mm, let me see. Did the addition of point oh 0.08, did that make a problem? Oh, I see what happened. Gotcha. Ah, anybody notice the careless mistake I made? I grabbed the wrong number. I tried to increase the diameter of the hole from the original hole diameter to 8.008 centimeters bigger than the original hole diameter, when in fact I wasn't supposed to use that. I was supposed to use, so here's the reason the answer didn't come out right. This number was, and this is just careless mistake, so y'all can correct it by just changing what this number is and working through it again, was supposed to be 6.445 centimeters plus 0.008 centimeters, which equals 6.453 centimeters. Now, when I do that, you can see what's going to happen is instead of dividing by 6.420 and getting the 1.001246, what I'm going to get is 6.453 divided by 6.420. That's going to give me instead 1.005140 equals 1 plus 12t minus dot dot dot. So that's the same thing there. But now what I want to do is subtract 1 from both sides and then add the 0.0024. So that's going to be 0.005140 plus 0.000240. That's going to give me a 0, an 8, a 3, a 5, a 0, 0.0. So that's the number that I'm going to divide by 12 times 10 to the negative 6. So I'll say minus, or actually I'll say plus 0.00024. Now I'm going to divide that 538 by 12 times 10 to the negative 6, and that gives me 448 degrees Celsius. That's the actual right answer. Sorry about that. Apologize for making that careless mistake. That was not helpful, but you've now seen twice how to do it. Hopefully that'll help you. Anybody have any questions on that? I'm very sorry again. All right, let's move on to the next one. So I left a little space at the top. That's mainly so I could use that volume formula. Specifically, delta V is equal to beta instead of alpha. V0 delta T. And it turns out that theoretically and experimentally, beta is approximately equal to 3 alpha, which is interesting because we live in a three-dimensional space world. So when we went from one dimension of linear expansion to three dimensions, it's neat that it happens to turn out to be three times as big. So that's what we're going to use here. I will tell you that the alpha for steel or iron, which are, remember, steel is, iron with some carbon and stuff like that added. But either way, you can treat it as steel, and that's 12 times 10 to the negative 6. And therefore, it turns out you would expect this to be 36, but it turns out that beta for iron is actually about 35 times 10 to the negative 6 reciprocal Celsius degrees. And it also turns out that beta for gasoline is about 950 times 10 to the negative 6 reciprocal Celsius degrees. So in this problem, it says an 80-liter gas tank is filled with gasoline at 18.0 degrees Celsius. The tank filled with gasoline sits in the sunlight and reaches a temperature of 41.1 degrees Celsius. How much gas will overflow the tank? Now, what's happening here is, remember, the volume, the air inside of the tank is going to act like we just cut a big solid chunk of iron and scraped out the inner iron parts, leaving the air, and that air is going to behave just like the inner iron parts were. So what's going to happen is the inner iron parts of the tank is going to expand, making it bigger than 70, or excuse me, bigger than 80.0 liters. And at the meantime, that's going to be a very small change because the coefficient of expansion is only 35 times 10 to the negative 6 for the volume expansion of steel. But the gasoline is going to experience a huge change because it's 950 times 10 to the negative 6. So what's going to happen is the tank expanding is going to make the overflow a little bit less. So what we're going to do is calculate the overflow of the gasoline and subtract from it the increase in volume of the tank. So let's start off by calculating the increase in volume of the actual gasoline. So delta V gas would equal 80.0 liters times 1 plus, now we're using gasoline, so this would be 950 times 10 to the negative 6. I'm going to leave off the units because it's just getting ugly. Okay, and the temperature now is going to be 41.1 degrees Celsius minus 18.0 degrees Celsius, like that. And that'll tell us how much the volume of the gasoline increased. So I'm going to do 950 times 10 to the negative 6 times parentheses 41.1 minus 18.0, close parenthesis. That is equal to 80.0 liters times 1 plus 0.02195. Now, obviously, we only had at best 3 sig figs there, so we would say this 5 is not a significant figure. But now we can add 1 to that, and now we can multiply it by 80.
Is that 950 times 10 to the negative 6?
Yeah, it is. That's a really big value for gasoline. So this means the change in volume. Uh, Oh, shoot. That's the final volume. Notice I used the formula. I said I was going to use the delta V, but I actually used the volume, the new volume one. So let me fix that right quick. That delta is not supposed to be there. If we have the delta, then we don't have the 1 plus. But if we don't have the delta, we have the 1 plus. So that's where that went awry. I apologize for that. But this result is 81.756 liters. Now, that was 3 sig figs times 3 sig figs, so we really should have only 81.7. is the volume of the gasoline now. Now, if the tank didn't change at all, that would mean 1.75 or 1.76 liters would overflow. But it turns out the volume of the tank did expand, and the amount it expanded is as follows. It's going to be a lot smaller, of course. So we got 80.0 liters times 1 plus 12 times 10 to the negative 6 times again 41.1 minus 18.0. Again, leaving off the units here. So 41.1 minus 18, that gives me 3 sig figs times 12 times 10 to the negative 6. That actually reduces me down to 2 sig figs. Adding that to 1, that gives me 1.0002772. Now I'm going to multiply that by 80, and that gives me 80.0222 liters. So overflow is the V gas minus the V tank, because the tank is the volume that it could actually hold. So if I take the 81.7556 minus 80.02, I get 1.73 liters, and that 3 is not a sig fig, so it's 1.7 liters roughly that overflows. Anybody have any questions on that? Feel free if you catch me making a mistake, like I suspect a lot of you saw that I had written delta V on the left, but actually worked out the right hand side of as if it wasn't delta V, because it was V equals V0 times 1 plus beta delta T. Probably some of you might have caught that. Feel free to speak up. I really, it doesn't offend me. It actually helps me, and it keeps me from making careless mistakes that makes life difficult for you guys. Any questions? All right. Now, the next part, we're going to talk about the ideal gas law. And I want to first point out what the gas laws were. Boyle gave us the first gas law, or I should say, is the first one we're covering. I can't remember historically. I think it was the first one we came up with, but it's also called the scuba diver's gas law. So the scuba diver's law is Boyle's law, and the rule that we normally interpret from that is never hold your breath, never hold your breath, never hold your breath. The reason why is Boyle's law says pressure and volume are inversely related. That means thumbs up, thumbs down behavior. This is the symbol that I use to talk about concepts. So, Boyle's law says that when the pressure goes up, the volume of the gas goes down. So, you can imagine, for instance, taking a balloon and it's like this big. And if the atmospheric pressure increased, it would shrink, but it's hard to see. What you can do, though, is take the atmospheric pressure and replace it with water pressure by submerging it under the water, and you would definitely conclude that the balloon would shrink in being pulled under the water, if you could even get it underwater. So Boyle's law says that pressure is inversely related to volume, which can also be interpreted as pressure times volume is equal to a constant. Now, with this goes the assumption that the other thermodynamic variables do not change, and there's really only two. It turns out three thermodynamic variables is enough to figure out the whole state of a gas, and the variables that you need are pressure, volume, and then something that's related to the number of moles, the number of atoms, the number of molecules, or the mass. So this is true for T equals a constant, and N or M or big N is constant. The lowercase m means the mass of the gas. The lowercase n means the number of moles of the gas. And the capital N means the number of molecules or the number of atoms of the gas. So that's Boyle's law. The next one is Charles's law. And Charles's law says that volume and temperature are directly related. So volume is directly related to temperature, which you can also write as V over T is equal to a constant. But in order for this to be true, you have to have for P and, well, let's say P and N R M R N equals a constant. Okay, so P has to be a constant, and M or N or N, big N has to be a constant, and that's Charles's law. There's also another one, and this is the Gay-Lussac law. So Gay was one last name, and the other guy's last name was Lussac, and I do remember them both being male, but if I'm wrong on that, by all means, correct me. So that's why I called them Guy. Sorry. Women have definitely contributed. It's just not in this particular case, and they might have, and we just didn't know it. But in this case, what it is, the pressure is directly related to the temperature, which can also be written as pressure over temperature equals a constant, but that's only true for, in this case, V equals a constant and N slash M slash N equals a constant. So you have to have a fixed amount of substance as well as a fixed volume. Now, you can combine all those ideal gas laws and make one big expression. What you'd get basically is pressure, volume over temperature equals a constant. And notice in all three of those ideal gas laws, we had different variables that were constant, but the one thing that was always constant was the number of moles or the number of atoms or molecules or the mass. And I think you can see that if you increase the number of moles or molecules or atoms, that the pressure and the volume would both tend to increase. So you can see that this would also imply that pressure times volume over temperature is equal to either the number of moles times a constant, or it could be the mass times a constant, or it could be the total number of molecules times a constant. And you'd be exactly right. It turns out the ideal gas law, as we stated, is PV is equal to N times R times T, and it has very specific rules. One, this is the number of moles of gas. Okay. And the number of moles can be found by taking the mass of the gas and dividing it by the molecular weight of the gas. Okay. Another rule is that this temperature must be in Kelvin. Okay. Another rule is this pressure has to be absolute, not not gauge pressure. Okay, gauge pressure, for instance, if you hold a tire gauge up against your valve stem on your car tire, when you push that little button in, air is free to leave through the tire pressure gauge. And what it does is it pushes out a little white piston that reads a measurement of certain number of psi, but it's pushing against atmospheric pressure. So the actual pressure of the tire is the pressure that that gauge reads plus atmospheric pressure. So that's really the difference. P absolute is equal to P gauge plus P atmosphere. So you have to know the atmospheric pressure as well. And that's basically it. The big thing also is that R, the ideal gas constant, in physics, we almost always use this value, which is 8.314 joules per mole Kelvin. But in chemistry, you'll occasionally run into using 0.0821 liters times atmospheres over mole Kelvin, or, and this is a fairly popular one, 1.99 calories per mole Kelvin. Those are the three versions you use. If you're using pressure in Pascal or pressure in newtons per square meter, those are the same thing. 1 Pascal is equal to 1 Newton per square meter. If you're using that pressure, then you need the 8.314. If you're using the pressure in atmospheres, then you need to use the 0.0821. So if P is in atmospheres, such that 1 atmosphere is equal to about 14.7 psi. It's also equal to 1.013 times 10 to the fifth Pascal. If you're using that, then you need to use the 0.0821. If you're using dynes per square centimeter, then you need to use 1.99. Okay, so that's where they're used. Now, let me go ahead and quickly show you at least one example because we only got about 5 minutes left. Hopefully, I can fit both of them in. But what is the volume of an ideal gas at standard temperature and pressure? Standard temperature and pressure, in case you hadn't heard that before, means 0 degrees Celsius, which you're not allowed to use Celsius, so you got to convert that to Kelvin, and it means a pressure of 1 atmosphere. Okay, so PV equals nRT, and they want to know what the volume is. So we write V is equal to nRT over P, which would be 1 mole. Oop, I left off a word. What is the volume of 1 mole of an ideal gas at standard temperature and pressure? So that's 1 mole times 8.314 joules per mole Kelvin times 273.15 Kelvin divided by 1.013 times 10 to the fifth Pascal. Okay. Now the Pascal is a Newton per square meter and a Joule is a Newton meter. So the Newton meter of the Joule has the Newton cancel out with the Newton and the Pascal, but the meter in the Joule multiplies by the meter squared in the Pascal to make cubic meters. So that's what the result is going to be. So I'll take 8.314 times 273.15, and then I'm going to divide that by 1.013 times 10 to the fifth Pascal, and that's going to give me 0.02242 cubic meters. Now, I will tell you that 1,000 liters is equal to a cubic meter, so this would also be 22.42 liters, and that's a figure that a lot of scientists and engineers just are going to expect you to know. Okay, the volume of 1 mole of an ideal gas at standard temperature and pressure is 22.4 liters. That's just something you should sort of know off the top of your head. This other one, which we're really only got 3 minutes left, a party balloon is filled with helium gas at 20 degrees Celsius and is approximately spherical with a diameter of 19.2. So volume for that is 4 thirds pi r cubed. And we want the diameter. We want to use the diameter. So I'm going to take that 19.2 and divide it by 2. So I'm going to say this is now 4 thirds times 3.14159 times 19.2 centimeters divided by 2 times 100 centimeters is equal to 1 meter. So that's going to give me it in cubic meters. So this volume is 1.33333 times 3.14159 times parentheses point zero, no, 0.192 divided by 2 in parentheses, and I'm going to cube that. And that gives me 0.003706 cubic meters. They know that the pressure is 1.03 atmospheres, which equals 1.03 times 1.013 times 10 to the fifth Pascal. I'd have to change the cubic meters to something else in order to use the atmosphere, and I could have actually used it as cubic centimeters and used the 0.0821, but or I could have converted it to liters, that is. But I'm not going to do that. So 1.03 times 1.013 times 10 to the fifth gives me 1.04 times 10 to the fifth Pascal. So I can finally say that the number of moles given by PV over RT is equal to 1.04 times 10 to the fifth Pascal times 0.003706. That's way too many sig figs, but the main thing is we've got the number. Okay. Divided by R, which is 8.314 joules per mole Kelvin times 293.15 Kelvin, 1.04 times 10 to the fifth times 0.003706. I'm going to divide that by parentheses 8.314 times 293.15, close parentheses. That gives me 0.1581 moles of helium gas. Now, helium has a mass of 4.00 grams per mole. So I can convert that to grams per mole just by multiplying that number by 4.00, and I can convert that to grams, excuse me, and that means the mass of the helium is equal to 0.6326 grams. That's it. You guys are free to go. I'm sorry I had to rush through these last two, but I got it done just 1 minute late. And as always, you guys are always free to leave at any time because it's optional that you even attend. But also, I know you have places to go. So thanks for coming, everyone. Please stick around if you have questions. Don't forget to chat me your first and last name if you haven't done so already. And have a great weekend. And let me know if you need any help with homework or any of that kind of stuff. We finished chapter 18, 17, by the way, so we'll start on 18 next time. Thank you, Nathaniel. You're welcome, Alexis. Thank you too, that is. Anybody else have any questions? Hey, Anahi, I see you made it. I know I'm probably overpronouncing your name. I apologize, but I'm glad you made it. Anahi. Matt, Alexis, you guys here still? Hey, Alexis. I see the wave. Hey. Anyone? All right. Well, I'm going to go ahead and stop sharing my screen and then sign off. It looks like everybody's gone. They're not replying or anything. Thanks for coming, everyone. Again, last time to ask me any questions if anybody has any. Doesn't appear that's happening. So have a good weekend, everybody. Thank you. Thanks again for coming.